Thank you very much for inviting me to the Future Schools Conference. I'm sorry I'm back here in England rather than with you in Australia. I'd really like to be there, but I hope I can transmit some of the thinking and ideas that we have in the video that will follow this. So I hope you have a great conference, and do follow me on Twitter at Conrad Wolfram, or go and look at our computerbasedmath.org site. I want to talk today about how we fix education for the AI age and some of the pretty profound changes I think need to happen for us to achieve this. Let's start by thinking about what are the effects of AI on the subjects in education. It changes what humans need to learn, but including what's for the computer and what's for the human. That interface between computer and human is not straightforward and is something new that we also have to adjust to. And as always, when we think about any change in education, the place to look to start with is what's happened in the real world and how can we replicate that change in education to best equip our students to enter that real world. So I wanted to start with an area that I believe is perhaps the most profound in the changes we're seeing with AI. And that is, how is ubiquitous computation changing real-world STEM? What is it? We've got this world now where we have computation available at all times, in our smartphones, on our computers, at all points in life. We have mechanized computation that has dramatically transformed our world in the last few decades. And the first question I want to ask is, how has that change manifested in the real world? What you might call maths, or perhaps nowadays computational thinking, is newly applied everywhere in a way that it never was before. Prototyping, linguistics, medical imaging, algorithmic trading, even archaeology, and of course biology, computational biology. These are areas that seemed way beyond the scope of mathematics applied to planets going around the sun and so forth. And yet these are areas that are now commonplace for the use of mathematics and computation every day. So data science is perhaps the one we're most familiar with in today's world. And it's quite dramatic to see how this has come forward in the last few years. What I'm going to try and do here is get the computer to go and decode the human gene. And you'll see here I actually entered a slightly too long a sequence, but what we're trying to look at is that sequence in the human genome, and I've called up in a few seconds how the chromosomes in the human gene match that particular sequence of base pairs I put in. The fact that I can do this data science from my desktop instantly is amazing change around from even a decade ago. This is the power of modern computation in data science. Data science is perhaps the largest everyday area that our students will immediately see for the use of computation. Analyzing data, working out what to do with it, getting answers from data. But of course, data is going to become more plentiful in more different areas, from whether it's our own collection of data as we do every day, or how that works with smart homes or government data. All of these things are very much prevalent and are growing at a rapid rate. So when we look at future skills for AI, one of the key things we have to think about is how we make citizen data analysts. All this data coming in and out, all these analyses that the computer is doing, all the ways in which the computer can help us. How can you as a human work with this, not get fooled by the data, be able to come up with better answers for your life, for your society, for your job? So one way to think about this is to break down what we need to do between what I would call survival skills and what I would call value add. See, survival skills in the Stone Age might have been how to make a fire to stop yourself being eaten by an animal. Nowadays, what are the survival skills? What are the things we need just to survive as individuals in a modern society, or to make the society survive? And at the same token, what are the things that really drive us forward? What are the things that are really worth value to our world? How are you going to make those top jobs and the top contribution that we hope our students are going to make? Now, I think that a core skill that underlies both of these survival skills and the value add is computational thinking. And if you like, computational thinking is a way of thinking about life which enables us to use the fantastic power that computation has given us, this system of logic, in a sense, and concepts and ideas that have been worked out over hundreds of years. Now, the core for learning about computational thinking, or what has been called mathematics or maths education, is indeed maths. That is the sort of core in our schools. And the question is computational thinking, this great skill we need for our populations, really manifested by maths education? Or has it somehow missed the mark? Well, I believe it has missed the mark and is dramatically continuing to do so. And I wanted to spend much of this talk describing why that was and how we get it back on track. When you look at maths education right now, there's a key central problem with it, in my view. I think it's about 80% the wrong subject. It isn't teaching these computational thinking skills we really need. And let's dig into why I say that. The key reason is because of the role of calculating in the middle of mathematics and computational thinking. See, in the outside world, in the last few decades, computers have taken over almost all the calculating. And they do much harder problems at much greater speed than humans can do. In education, we have students doing almost all the calculating. Most of maths education is about how to calculate, not how to use mathematics as a problem-solving discipline into which calculating by computer or human can be done. And so we have a situation where about 80% of the school subject doesn't match the outside world, because 80% of it is about calculating, not about problem solving with the best equipment for that, which may be human or more commonly a computer. So computers are the central difference that has separated today's outside computational thinking and maths from the educational maths that we have. But it's also applying computers to do that outside subject, not just to improve the teaching of today's subject. Let's zoom out for a moment. Why are we learning maths? Well, I think there are three good reasons. Technical jobs that so empower individuals and our societies. What one might call everyday living, just the ability to survive, be able to do basic quantitative skills, what's sometimes called numeracy, analyze government data that comes out. Do you believe what you're being told? Does the graph make sense to you? Should you take this mortgage or that mortgage? Those are everyday mathematical skills that we increasingly need. And thirdly, what might be called logical mind training. Can we think logically about life, whether explicitly about maths or not? And that last skill affects all sorts of things like democracy. Do you believe arguments that are being put by different candidates in elections? Or can you dismiss them because you understand the failure of their logic? These are all crucial parts of what I think mathematics education should be teaching. What is mathematics? Well, really, it's a four-step process where you firstly define questions. You secondly translate those questions, those real questions. For example, if I talk for too long in this room and I've switched the ventilation off, how long can I survive on the oxygen that I have? That would be a question. I might now want to translate that to mathematical abstraction. Why do I do this? Well, because abstract mathematics gives us tremendous power to do stage 3, which is to go from that question to an answer, a real definite answer. And we have hundreds of years of experience in doing that. And then we can go the other way and interpret the result. We'll say that the answer was x equals 3. Maybe I can survive for 3 hours. Now we need to go back and do that translation I just did. What x equals 3 means I can survive for 3 hours, or maybe I need to question that. Did I get the right answer, or was somehow the answer flawed? Here's the problem. In maths education, we're spending almost all our time doing step 3 by hand, and we are drowning out these other steps that are so critical to future mathematics and computational thinking in the outside world. Here's an example I love to give. Here's a very simple equation, which most people at school have to solve something like this, a linear simultaneous equation. But you see, even though this is an equation, the computation could get much harder without the basic understanding of the equation changing. So I've changed that to a cubic equation. That's a much harder equation to solve. Normally people at school don't get to doing this at all, but yet the understanding of what you need to abstract this is to an equation hasn't changed. We just put harder algebra in it. This is the sort of thing we need where we have computers and humans going together. And it gets even worse than this. That's me, hello, good to see you again. I'm now going to talk to my phone and see if I can get it to do this equation. Solve x cubed plus 2 equals 2y and y minus x equals 5. You'll see here that I have actually managed to solve this equation, if you can see on the video, and this is in our Wolfram Alpha technology through Apple's Siri, and it's actually managed to solve this equation just by talking to the phone. If I can do that by talking to my phone, an equation that most students can't solve after years of school, you've got to ask why that's what we're teaching them rather than the higher level problem solving I'm talking about. One of the things that I think is so important when we educate people for computational thinking is to start with an actual problem that they might be interested in. What's the perfect password for your login? Am I normal? Is fraud occurring? What's a beautiful shape? These are all actual real problems. And traditionally we start instead with the abstract issue, not the problem itself. Here's an example problem. Can I spot a cheat? Well, in this example I'm going to type heads and tails, or H and T, into my computer, and what we've done often is to divide a class into two sets, one that types it in like I've done, i.e. cheats, and the other who actually do the experiment with a coin and note down the results. And the question is, can the teacher tell who's cheated and who hasn't? So let me show you the results here. I actually only passed one of the tests, so I think if I were the teacher I'd be pretty sure that this was a cheat. But instead you could contrast that to, I'm going to semi-cheat, I'm going to get the computer to generate 200 random integers, and I'm then going to paste those in. These are ones and zeros rather than H's and T's, but I think the software will manage to interpret them. And so I'm just going to paste these into to here, and we'll see now whether, in fact, the computer passed all 5 tests. So that's equivalent. That's the computer doing a simulation and me doing the coin toss. So I guess it's a semi-cheat, but it shows the difference. That isn't this amazing that by doing some data analysis, we can spot whether somebody's cheating or not, potentially. And this is the sort of basis, very simplistically, but the basis of bank credit card fraud detection and things like that. So this is the sort of real-life application that students can often get hold of and understand how it affects their lives, why mathematics is relevant to things they might actually do. But you see, you can only do this with a computer. You couldn't do this sort of data analysis by hand. It wouldn't make sense. And so we absolutely need computers to give us real techniques, real understanding of actual things that we might use mathematics for. Here's another example. At Computer-Based Maths, we've been building modules, so-called, to help students through understanding different kinds of things. So this module is about how fast could I cycle a stage of the Irish equivalent of the Tour de France cycle race. We were working on this module with Ireland, which is why we have this unusually named race here. And I just wanted to walk you through a few things in this. We've tried to structure this module. This is the teacher edition of it, which fits with the student edition, so that you can actually see different what the teacher suggested what the teacher should do, as well as indeed what the student should do. So these orange boxes here tell the teacher how you could help the teacher to conduct the lesson, and we've got lots of things like the steps you might go through and outcomes you're trying to achieve and so forth. These are not present in the student version. However, what's below is. So this is an example of modeling. And we start off this module by saying, here are all the things. We built a nice model for you about cycling. And can you use this model to work various things out about how you might go faster when you're biking? and can you answer various questions underneath here about it. So this is an early step into modelling, and it's also part of evaluating whether you believe the model. Much later on in this module, we go to having students actually build their own model, testing their own frontal area for wind resistance. And this is where, for example, they're doing image recognition on themselves to figure out whether they can reduce their wind resistance. And later we actually have them building some code to test what would happen when you load data in, for example, from Google Maps to test around your own cycling track. So this is examples of what maths, computer-based maths, really could be about if we change our view of calculating as the central piece by hand of mathematics. Now I wanted to talk briefly about how computational thinking, mathematics and coding might fit together. I think of computational thinking as a way that we do life, and STEM indeed, but life more generally. Maths, in a sense, is computational thinking with a particular area of domain knowledge that's grown up over the last few years. And coding, in a sense, is a way to express that computational thinking or maths. It's a very important part of what we do. And I was just going to do a very simple example for you here. It's me again. And I thought by this point you were probably getting a bit tired of me in the giving the talk. So I thought what I would do is set an image of me to be me, as you see, and then say I would like to show me together with an image of me blocked out. So what I want to do is draw a rectangle around me. So I'm going to do a rectangle applied to find faces on me. And I'm going to, I think I need to put graphics around this. So this is a typical example of programming. And what's nice is that I can actually try and show you this and see whether I can get it working here and now. And there you see, in a few lines of code, I managed to actually block my face out. And you see that's the sort of thing you can do by combining high-level mathematics, which includes algorithms to find faces, with coding. And that's the sort of thing where I think high-level coding expresses mathematics and computational thinking. A crucial part of what we have to do to help people learn computational thinking is to fix motivation. You know, too many of our students get turned off by mathematics. And you can see why. They're given abstract thoughts first, before they're given real-life problems to solve, things that don't seem to relate at all to their lives. Now, there are some students who really like the abstraction first, but it's a very small number. Most it scares off. And in fact, abstraction is, as I've explained with my 4 steps, step 2, abstraction, is a really important step. I just wouldn't do it first. I would start with messy, hard problems and use the mathematics and the abstraction to get that problem solved and to show students how we can help with that. So one of the questions you might ask are, what are the core outcomes we need from mainstream mathematics in order to engender computational thinking? And I won't go through this in detail, but you'll see from the link at the top, computerbasedmath.org, our site, has on it required outcomes from mainstream maths. And we've really rethought what these should be. And they're things as diverse as managing computations, confidence to tackle new problems, as well as things like communicating and collaborating. There's a very wide range of outcomes I think we need, and we need to recast our maths in a way that, that enables those to be really shown through. Good news is that the recent change in the Australian curriculum, I think our work on outcomes fits very nicely and cleanly, in fact, with the new dimensions of the Australian curriculum. And here we've tried to color code our 11 dimensions together with the sort of cube that represents the Australian curriculum. And we've been working with various bodies in Australia to try and understand how those fit together and how we can really enhance some of these areas of the curriculum that has been laid out across Australia, and of course fitting in with each of the states' education policies. So my real message here in this talk is we have a new power of automation. You know, this has happened before in human history. We had mechanization in earlier industrial revolutions where physical mechanics helped to do jobs that we'd previously done ourselves as humans. We've now got a situation where AI fundamentally changes the place where humans should be in terms of what they need to do relative to what computers and AI can do. And the question is, what is our reaction to that in education? In my view, there should only be one possible reaction, which is we need to stand on that power of automation and go further as humans. We need to learn how to interact with that AI. We need to learn how to fix how we learn what we learn, not to compete with the machines, but to go further. And a pretty dramatic change is needed in order for us to achieve that. And the change is needed in the subjects, and particularly the subject of mathematics, which has been our mainstream technical subject through education, which currently isn't meeting the needs of this new era. And the mistake is to think somehow we should learn what the machines do and try and replicate that machinery, which is kind of what we're doing at the moment. We don't want third-rate human computers. We want first-rate human problem solvers in this new AI age. Years ago, when we first released our software Mathematica, Steve Jobs, whose next machines we will bundle on, came up with a quote. And it is rather interesting to look back at this. He said, "Mathematica will revolutionize the teaching and learning of math by focusing on the prose of mathematics without getting lost in the grammar." I put will in red because I think what he should have said is should. This should have happened right back after 1988, but it didn't, and it hasn't yet. And that is the urgent requirement now that we need to achieve. The question we've all got to ask ourselves is, are our societies, are our individual students ready and prepared for the computational knowledge economy? I'm arguing that particularly with computational thinking, we haven't got there. And that's a crucial part to this new economy. I call it computational knowledge economy. It's sort of a step beyond the knowledge economy that Drucker and others talked about. This is an economy in which most people are interacting with AIs, and that the value add is in working with those AIs, not in trying to somehow do their job. And I think, as I said, the answer is we haven't yet got there. No country's got there. And the question is, can Australia lead this change? And I think there's great appetite in many of the states I've talked to in Australia and federally, and with bodies like ACARA, for example, for this change to occur. But it's very difficult in the ecosystem of education to get change to happen anywhere in the world. You've got to align schools and teachers and parents and governments and people's views as to what needs to change, and the change itself is complicated. But I think there is a real opportunity in Australia and in the individual states that are very forward-looking and actually beyond many other countries in the world. And I know there's a concern in Australia for making sure we really do set people up for life, for a real working career and these top value-added jobs, as well as for their survival skills. So I'd urge you all, at whichever part of the educational ecosystem you operate, really to press for change, because only if everyone presses for change can we really make that change happen. And certainly we're very keen to help for the part that we can play in understanding and building out some of that change as it's possible. And, you know, part of course, that change needs to happen is assessments that lock everything as to what people learn need to change alongside how we're doing the rest. But I think all of those things can happen in concert if everyone is minded to do that kind of change. So thank you very much. I'm very sorry again I couldn't be with you in Australia, but I hope you can help to move this change forward and help us in this endeavour to fix maths, fix education for the new AI age. Thank you.